CIET NCERT presents audiobook Ganita Manjari Part 1, Textbook of Mathematics for Grade 9.
Chapter number 2, Introduction to Linear Polynomials. On the right side of the page, you are provided with a QR code, scanning which you can reach out to the additional resources to this chapter. 2.1 Introduction. We have learned about algebraic expressions in earlier classes. In this chapter, we will learn about the special types of algebraic expressions called linear polynomials. Let us first consider a few examples of algebraic expressions. Example 1. Raju went to a shop where there were sealed boxes of different colors on sale. The shop owner told him that the red boxes have 4 pence each and the blue boxes have 5 pence each. Now, if Raju bought X red boxes and Y blue boxes, how can he quickly figure out the total quantity of pens and pencils? Also, if he got 3 extra pens free, how many pens and pencils did he get altogether? Here in figure 2.1, you are provided with 2 boxes. One is red in color, which has 4 pens, and the other is blue in color, which has 5 pencils. Observe that X red boxes will have 4x pens and Y blue boxes will have 5Y pencils. Also, he got 3 extra pens free. Thus, the total number of pens and pencils is given by the algebraic expression 4x plus 5y plus 3. In this example, 4x, 5y and 3 are terms of the expression. X and y are letter numbers. The numbers 4 and 5 are the coefficients of x and y, respectively, and 3 is a constant. From now onwards, we will use a widely used alternate word for letter numbers, variables. Thus, in the expression 4x plus 5y plus 3, we say that the variables used are x and y. Example 2. A rectangular garden of length L meters and width W meters has to be fenced and decorated. A wire fence is to be laid along the length costing 100 rupees per meter, and a wooden fence is to be built along the width costing 80 rupees per meter. Special seeds have to be sown throughout the garden, which will cost 50 rupees per square meter. Page number 17. Here we can find a picture of a rectangular garden of length L and width W in figure 2.2. What will be the total cost incurred? Cost of wire fencing along the garden length is equal to 2L into 100 is equal to 200 L rupees. Cost of wooden fencing along the garden width is equal to 2W into 80, that is equal to 160 W rupees. Cost of sowing seeds throughout the entire garden depends on the area, is equal to 50 into L into W, that is equal to 50 LW rupees. Total cost is equal to 200 L plus 160 W plus 50 LW rupees. Thus, 200 L plus 160 W plus 50 LW is the algebraic expression for the total cost. Think and reflect. Question number 1. Can you identify the terms, variables and coefficients of this algebraic expression? Question number 2. How is it different from the algebraic expression in example 1? Example 3. A wire of length 20 centimeters is bent in different ways to form rectangles. For example, we can have a rectangle with length 7 centimeters and width 3 centimeters. We can also have one of length 5.5 centimeters and width 4.5 centimeters. Think of a few more ways of forming such rectangles. Can you write an expression for the area of such rectangles? If length of the rectangle is x centimeters, then the width is 10 minus x centimeters. The expression for the area of these rectangles is x into 10 minus x, or 10x minus x square. Think and reflect. Question number 1. Can you identify the terms, variables and coefficients of this algebraic expression? Question number 2. Can you point out any similarity or difference between the algebraic expressions obtained in examples 1 and 3? Page number 18. Note that the algebraic expressions in example 1 and example 2 involve two variables, whereas the algebraic expression in example 3 involves only one variable. Expressions such as 4x, x square plus 1, 2y minus 5, 5y cube plus y square plus 2y minus 1, 3z plus 7 are algebraic expressions that involve only one variable, x, y or z. In this chapter, we will restrict our discussion to algebraic expressions involving only one variable. You may have noticed that in an algebraic expression, the powers of a variable also appear. For example, in the expression x square plus 5x plus 1, the highest power of x is 2, whereas in the expression 5y cube plus y square minus 8, the highest power of the variable y is 3. Further, in the expression 5y cube plus y square plus 2y minus 1, the coefficient of y cube is 5. That of y square is 1. That of y is 2. And the constant term is minus 1. Such algebraic expressions involving one variable and its powers are called one-variable polynomials, univariate polynomials, or, when the context is clear, simply polynomials. Univariate means having one variable. The highest power of the variable in a polynomial is called its degree. For example, first 5y cube plus y square plus 2y minus 1 is a polynomial of degree 3. Such polynomials are called cubic polynomials. Second, x square plus 5x plus 1 is a polynomial of degree 2. Such polynomials are called quadratic polynomials. Third, 3z plus 7 is a polynomial of degree 1. Such polynomials are called linear polynomials. Fourth, the constant 8 is a polynomial of degree 0, as it can be written as 8x to the power 0, in which the power of the variable x is 0. Such polynomials are called constant polynomials. Exercise set 2.1. Question number 1. Find the degrees of the following polynomials. First part, 2x square minus 5x plus 3. Second part, y cube plus 2y minus 1. Third part, minus 9. Fourth part, 4z minus 3. Question number 2. Write polynomials of degrees 1, 2 and 3. Question number 3. What are the coefficients of x square and x cube in the polynomial x to the power 4 minus 3x cube plus 6x square minus 2x plus 7? Page number 19. Question number 4. What is the coefficient of z in the polynomial 4z cube plus 5z square minus 11? Question number 5. What is the constant term of the polynomial 9x cube plus 5x square minus 8x minus 10? Recall that polynomials of degree 1 are called linear polynomials. In this chapter, we shall study linear polynomials. 2.2 Linear polynomials. We begin with some examples involving linear polynomials. Example 4. The perimeter of a square of side x is 4x, which is a linear polynomial in the variable x. Think and reflect. Find the perimeter of squares with sides 1 cm, 1.5 cm, 2 cm, 2.5 cm and 3 cm. What will happen to the perimeters if the sides increase by 0.5 cm? Example 5. A chess club charges a joining fee of 200 rupees plus 50 rupees for every match played. The following table reflects the amount a player will have to pay as the number of matches varies. Here we are given a tabular column which depicts the number of matches played and the amount paid. When the number of match played is 1, the amount to be paid is 250 rupees. For 2 matches, it is 300 rupees. For 3 matches, 350 rupees. For 4 matches, 400 rupees. For 5 matches, 450 rupees, and so on. For m matches, 200 plus 50m is to be paid. Hence, if m is the number of matches played, the total cost will be 200 plus 50m rupees. Observe that 200 plus 50m is a linear polynomial in the variable m. The amount paid increases by the constant value of 50 rupees for every additional match played. Think and reflect. If a player paid 750 rupees, how many matches did he play? The examples given here highlight a characteristic feature of linear polynomials, that the difference between the successive values for integer inputs is constant. In example 4, the perimeters increase by 2 centimeters each time. The side of the square increases by 0.5 centimeters. Page number 20. Similarly, in example 5, the amount paid by a player increases by 50 rupees for every additional match played. Such patterns are called linear patterns. When we equate a linear polynomial in one variable to a constant, we get a linear equation. Let us consider the following example. Example 6. The sum of two numbers is 64. One of the numbers is 10 more than the other. What are the two numbers? Let the smaller number be x. Then the larger number must be x plus 10. Since their sum is 64, we have the linear equation x plus within brackets x plus 10 is equal to 64. This implies that 2x plus 10 is equal to 64. Note that 2x plus 10 is a linear polynomial. By equating it to 64, we get a linear equation 2x is equal to 54 or x is equal to 27. The numbers are therefore 27 and 37. Polynomials can also be thought of as an input-output processes. For instance, consider the linear polynomial 2x plus 3. For every x, there is a corresponding value of the polynomial 2x plus 3. For instance, if x is equal to 4, we substitute 4 in the expression to get 2 into 4 plus 3 is equal to 11. If x is equal to minus 6, then we substitute minus 6 in the expression to get 2 into minus 6 plus 3, that is equal to minus 9. Figure 2.3 depicts this process as an input-output machine where the input is the value of x and the output is the value of 2x plus 3. This process can be referred to as a function where the expression 2x plus 3 is a function of the variable x. You will learn more about functions in later grades. We have figure 2.3, a linear expression as an input-output process. Here, there is a picture of a machine with an input and an output display. Input display reflects x is equal to 4. Output display reflects y is equal to 11. And the display on the screen of the machine is y is equal to 2x plus 3. Think and reflect. We have learned that to evaluate the value of an algebraic expression, we substitute a value of the variable in the given expression. Consider example 3, where the wire is bent to form a rectangle. Here, the area of the rectangle 10x minus x square is a function of x. Can you interpret this as an input-output process? What value does the expression take when x is equal to 6 centimeters? Page number 21. Note that 2x plus 3 is a linear function, whereas 10x minus x square is a quadratic function. Exercise set 2.2. Question number 1. Find the value of the linear polynomial 5x minus 3 if first part x is equal to 0, second part x is equal to minus 1, third part x is equal to 2. Question number 2. Find the value of the quadratic polynomial 7s square minus 4s plus 6 if first part s is equal to 0, second part s is equal to minus 3, third part s is equal to 4. Question number 3. The present age of Salil's mother is 3 times Salil's present age. After 5 years, their ages will add up to 70 years. Find their present ages. Question number 4. The difference between two positive integers is 63. The ratio of the two integers is 2:5. Find the two integers. Question number 5. Ruby has 3 times as many 2 rupee coins as she has 5 rupee coins. If she has a total 88 rupees. How many coins does she have of each type? Question number 6. A farmer cuts a 300 feet fence into two pieces of different sizes. The longer piece is 4 times as long as the shorter piece. How long are the two pieces? Question number 7. If the length of a rectangle is 3 more than twice its width and its perimeter is 24 centimeters, what are the dimensions of the rectangle? 2.3. Exploring linear patterns. Observe the following growing pattern of square tiles. Here in figure 2.4, we have a growing pattern of square tiles, which reflects at stage 1 we have 1 square tile, in stage 2 we have 3 square tiles, in stage 3 we have 5 square tiles arranged, and in stage 4 we have 7 square tiles arranged. Page number 22. Think and reflect. Predict the number of squares in the next 3 stages of the pattern and write the sequence of numbers up to stage 7 of the pattern. Each stage is obtained by adding 2 more tiles to the previous stage. The table mentions the number of tiles for the first 7 stages. We have a tabular column here which reflects the stage and number of square tiles used. We have the stages as follows: 1, 2, 3, 4, 5, 6 and 7, and the corresponding number of tiles are 1, 3, 5, 7, 9, 11 and 13. To generalize this pattern, we observe that the number of squares at each stage is 1 less than twice the number of the term. For example, in term 2, the number of squares is 2 into 2 minus 1, that is equal to 3. In term 5, the number of squares is 2 into 5 minus 1 is equal to 9, and so on. This leads us to conclude that the number of squares at stage n is given by 2n minus 1. The polynomial 2n minus 1 has degree 1. Hence, it is an example of a linear polynomial. Also, the difference between consecutive terms in the sequence of the number of squares, that is 1, 3, 5, 7, 9 and so on, is the constant value 2. Thus, with each stage, the number of squares increases by 2. The relationship between the number of the stage and the number of square tiles is a linear relationship. Think and reflect. Using the expression 2n minus 1, can you find out how many tiles will be there in the 15th stage and the 26th stage of the pattern? Also, which stage will contain 21 tiles and 47 tiles? Example 7. Bella has 100 rupees for pocket money. She spends 5 rupees every day. After how many days will she be left with 40 rupees? Here we have a tabular column reflecting the day number and the amount left in rupees. For day 0, the amount left is 100 rupees. For day 1, 100 minus 1 into 5, that is equal to 95 rupees. For day 2, the amount left is 100 minus 2 into 5, that is equal to 90. For day 3, the amount left is 100 minus 3 into 5, that is equal to 85 rupees. For day 4, amount left is 100 minus 4 into 5, that is equal to 80 rupees. Page number 23. Observe that the amount left on the nth day will be 100 minus 5 into n rupees. Therefore, on the 12th day, the amount left will be 100 minus 12 into 5 rupees, that is equal to 40 rupees. Think and reflect. What amount will be left on the 15th day? How many days will it take for the entire amount to be spent? Example 8. An auto rickshaw fare starts at 25 rupees and remains the same for the initial 2 kilometers. Then it increases by 15 rupees per kilometer. What will be the fare for a travel of 10 kilometers? For the initial 2 kilometers, the fare is 25 rupees. For every kilometer, that is km in brackets, thereafter the fare will increase by 15 rupees. Therefore, the total fare for the travel of 10 kilometers will be 25 rupees plus 15 into 8, that is equal to 145 rupees. Here we have a tabular column reflecting kilometers travelled and the fare mentioned in rupees against them. For 1 kilometer, the fare is 25 rupees. For 2 kilometers, the fare is again 25 rupees. For 3 kilometers, fare is 25 plus 1 into 15, that is equal to 40 rupees. For 4 kilometers, the fare is 25 plus 2 into 15, that is equal to 55 rupees. For 5 kilometers, the fare is 25 plus 3 into 15, that is equal to 70 rupees. For 6 kilometers, the fare is 25 plus 4 into 15, that is equal to 85 rupees. Observe that the total fare for a travel of n kilometers will be 25 rupees plus 15 into n minus 2, that is equal to 15 minus 5, where n is greater than or equal to 2. Here, the fare for a specific distance covered is a function of the distance n kilometers. Think and reflect. For how many kilometers will the fare be 130 rupees? Note that in all the above examples, the nth term is a linear expression in n. A linear pattern is a sequence of numbers where the difference between two consecutive terms is constant. We will learn more about linear patterns in the chapter on sequences and progressions. Exercise set 2.3. Solve the following. Question number 1. A student has 500 rupees in her savings bank account. She gets 150 rupees every month as pocket money. How much money will she have at the end of every month from the second month onwards? Find a linear expression to represent the amount she will have in the nth month. Page number 24. A rally starts with 120 members. Each hour, 9 members drop out of the group. How many members will remain after 1, 2, 3 and so on hours? Find a linear expression to represent the number of members at the end of the nth hour. Question number 3. Suppose the length of a rectangle is 13 centimeters. Find the area if the breadth is first part 12 centimeters, second part 10 centimeters, third part 8 centimeters. Find the linear pattern representing the area of the rectangle. Question number 4. Suppose the length of a rectangular box is 7 centimeters and breadth is 11 centimeters. Find the volume if the height is first part 5 centimeters, second part 9 centimeters, third part 13 centimeters. Find the linear pattern representing the volume of the rectangular box. Question number 5. Sarita is reading a book of 500 pages. She reads 20 pages every day. How many pages will be left after 15 days? Express this as a linear pattern. 2.4 Linear growth and linear decay. Linear expressions help to model situations or phenomena where there is growth or decline. Consider the following examples. Example 9. The cost of a journey is given by the linear function c within brackets d is equal to 100 plus 60 into d, where c indicates total cost in rupees and d the distance travelled in kilometers. Let us make a table of values for d varying from 0 to 10 kilometers and explain how the cost increases for every kilometers. Here we have a tabular column reflecting the distance travelled d in kilometers and cost c in rupees. For 0 kilometers, the cost is 100 rupees. For 1 kilometer, the cost is 160 rupees. For 2 kilometers, the cost is 220 rupees. For 3 kilometers, the cost is 280 rupees. For 4 kilometers, the cost is 340 rupees. For 5 kilometers, the cost is 400 rupees. In this example, as the value of d increases by 1 kilometer, the value of the cost function c increases by a fixed amount of 60 rupees. This is an example of linear growth. Think and reflect. What is the cost for travelling 15 kilometers? For how many kilometers will the cost of the journey be 700 rupees? Example 10. The height of water in a cylindrical tank is 3 meters at the start of summer. The height h meters at the end of t months is given by the linear function h within brackets t is equal to 3 minus 0.5 into t. Page number 25. We have a tabular column here which reflects the month in t and height h in meters. For 0, the height is 3 meters. For 1 month, the height is 2.5 meters. For 2 months, the height is 2 meters. For 3 months, the height is 1.5 meters. For 4 months, the height is 1 meter. In the example here, as the value of t increases by a fixed number, that is 1 month, the value of the height h decreases by a fixed number 0.5. Therefore, this example represents linear decay. Think and reflect. What will be the height of the water at the end of 5 months? Linear growth describes a linear pattern where a quantity increases by a constant amount over equal intervals. Similarly, linear decay describes where a linear pattern where a quantity decreases by a constant amount over equal intervals. Exercise set 2.4. Question number 1. Suppose a plant has height 1.75 feet and it grows by 0.5 feet each month. First part, find the height after 7 months. Second part, make a table of values for t varying from 0 to 10 months and show how the height h increases every month. Third part, find an expression that relates h and t and explain why it represents linear growth. Question number 2. A mobile phone is bought for 10,000 rupees. Its value decreases by 800 rupees every year. First part, find the value of the phone after 3 years. Second part, make a table of values for t varying from 0 to 8 years and show how the value of the phone v depreciates with time. Part 3. Find an expression that relates v and t and explain why it represents linear decay. Question number 3. The initial population of a village is 750. Every year, 50 people move from a nearby city to the village. First part, find the population of the village after 6 years. Page number 26. Second part, make a table of values for t varying from 0 to 10 years and show how the population p increases every year. Third part, find an expression that relates p and t and explain why it represents linear growth. Question number 4. A telecom company charges 600 rupees for a certain recharge scheme. This prepaid balance is reduced by 15 rupees each day after the recharge. First part, write an equation that models the remaining balance b within brackets x after using the scheme for x days. Explain why it represents linear decay. Second part, after how many days will the balance run out? Third part, make a table of values for x varying from 1 to 10 days and show how the balance b within brackets x reduces with time. 2.5. Linear relationships. A linear relationship represents the relationship between two variables x and y and can be expressed as y is equal to ax plus b. Let us revisit the growing pattern of square tiles in figure 2.4. If x represents the number of the term and y represents the number of square tiles, then the linear relationship between x and y is expressed as y is equal to 2x minus 1. Sometimes we may be required to find the linear relationship between two quantities. Example 11. A telecom company charges a fixed monthly fee and an additional cost per GB of the internet data used. A student observes that when she used 10 GB, her bill was 350 rupees. When she used 20 GB, her bill was 550 rupees. If the monthly bill y depends on the amount of data used, x in GB, according to the relation y is equal to ax plus b, find the values of a and b. Note that x is equal to number of GB of the internet data used and y is equal to total monthly cost in rupees. To find the linear relationship, y is equal to ax plus b, we note that when x is equal to 10, y is equal to 350. Also, when x is equal to 20, y is equal to 550. We substitute these in y is equal to ax plus b to arrive at the following equations. 350 is equal to 10a plus b and 550 is equal to 20a plus b. We solve these as follows. Let b is equal to 350 minus 10a. From the first equation, we substitute this in the second equation to obtain 550 is equal to 20a plus 350 minus 10a. Thus, 550 is equal to 10a plus 350, or 10a is equal to 200. So, a is equal to 20. This leads to b is equal to 350 minus 10a, that is equal to 350 minus 200, that is equal to 150. Page number 27. We substitute the values of a and b in the equation y is equal to ax plus b to obtain y is equal to 20x plus 150. Thus, y is equal to 20x plus 150 represents the linear relationship between y, the bill amount in rupees, and x, the number of GB of the internet data used. Think and reflect. Can you guess what the numbers 20 and 150 in the equation y is equal to 20x plus 150 represent? Exercise set 2.5. Question number 1. A learning platform charges a fixed monthly fee and an additional cost per digital learning module assessed. A student observes that when she assessed 10 modules, her bill was 400 rupees. When she assessed 14 modules, her bill was 500 rupees. If the monthly bill y depends on the number of modules assessed x, according to the relation y is equal to ax plus b, find the values of a and b. Question number 2. A gym charges a fixed monthly fee and an additional cost per hour for using the badminton court. A student using the gym observed that when she used the badminton court for 10 hours, her bill was 800 rupees. When she used it for 15 hours, her bill was 1100 rupees. If monthly bill y depends on the hours of the use of the badminton court x, according to the relation y is equal to ax plus b, find the values of a and b. Question number 3. Consider the relationship between temperature measured in degrees Celsius, that is in brackets degree C, and degrees Fahrenheit within brackets degree F, which is given by degree Celsius is equal to A degree Fahrenheit plus B. Find A and B. Given that ice melts at 0 degrees Celsius and 32 degrees Fahrenheit and water boils at 100 degrees Celsius and 212 degrees Fahrenheit. Hint: when degree Celsius is equal to 0, degree Fahrenheit is equal to 32, and when degree Celsius is equal to 100, degree Fahrenheit is equal to 212. Use this information to find A and B, and thus the linear relationship between degree centigrade and degree Fahrenheit. 2.6 Visualizing linear relationships. As we have noticed in many examples in this chapter, a linear pattern or relationship can be expressed in the form of an equation y is equal to ax plus b. Now, we shall learn to plot such an equation as a straight line. To plot a linear equation, we need to identify any 2 points on the line. For example, to plot y is equal to 2x plus 1, we may identify 2 points as follows. Page number 28. When x is equal to 0, y is equal to 1. So, 0, 1 is a point on the line. We can call this point A. We say that the x coordinate of A is 0 and the y coordinate is 1. Also, when x is equal to 3 and y is equal to 7, thus B 3, 7 is another point on the line. We plot these points on the coordinate plane. Join them and extend the line in both directions as given in figure 2.5. Here in figure 2.5 we have a graph sheet on which the straight line y is equal to 2x plus 1 has been drawn. We have an x-axis with points marked as -2, -1, 0, 1, 2, 3, 4, 5, and on y-axis we have the points marked as 1, 2, 3, 4, 5, 6, 7, 8. And we also have point A marked on the graph paper as A01 and point B as 3, 7 and a line joining these 2 points. Think and reflect. Identify other points on the line by completing the following table. We are given a tabular column in which we have the values of x and y. The values of x mentioned are 1, 2, 5, 7, 9, 12, 20. And values of 2 columns are given. Others are left blank for you to fill up. For 1, the value of y is 3. For 7, the value of y is 15. Note that 1, 3 and 7, 15 are also the points on the line y is equal to 2x plus 1. Plot the points on the line. You may use a graph paper for this task. Observe that if a point lies on a line, its coordinates must satisfy the equation of the line. Thus, we can verify that 7, 15 lies on the line y is equal to 2x plus 1 by substituting x is equal to 7 and y is equal to 15 in the equation. Example 12. Let us plot the points -1, -3, 0, 0, 1, 3, 3, 9, 4, 12 in the coordinate plane on a graph paper as given in figure 2.6. Join the points -1, -3 and 4, 12 using a ruler. Doing so, observe that all 5 points lie on a straight line. Can you guess the equation of this line by looking at the relationship between the x and the y coordinates of each point? Page number 29. Here we are given the graph in figure 2.6. The points marked on x-axis are -12, -10, -8, -6, -4, -2, 0, 2, 4, 6, 8, 10, 12, 14, 16, 18 and 20. On y-axis, the points marked are -4, -2, 0, 2, 4, 6, 8, 10 and 12. We can also find the points plotted on the graph as 4, 12, 3, 9, 1, 3, 0, 0 and -1, -3. For each point, the value of the y coordinate is 3 times that of the x coordinate. We can therefore say that y is equal to 3x. Example 13. Let us plot the points -3, 6, -2, 4, 0, 0, 1, -2, 2, -4, 3, -6 in the coordinate plane on a graph paper as given in figure 2.7. Join the points -3, 6 and 3, -6 using a ruler. Doing so, observe that all 5 points lie on a straight line. Can you guess the equation of this line by looking at the relationship between the x and y coordinates of each point? Here in figure 2.7, we have a graph sheet on which the points of x-axis are marked as -12, -10, -8, -6, -4, -2, 0, 2, 4, 6, 8, 10 and 12. On y-axis, we have the markings as -6, -4, -2, 0, 2, 4 and 6. The points plotted on the graph sheet are 3, -6, 2, -4, 1, -2, 0, 0, -2, 4, -3, 6. Example 14. Draw the graphs of y is equal to 1 upon 2x, y is equal to x, y is equal to 2x by selecting suitable points on these lines. The hint provided is, in order to graph y is equal to 1 upon 2x, we could take the points 0, 0 and 4, 2. Can you verify that these lie on the line? Page number 30. Figure 2.8. The graphs of these linear equations without any points labeled. In the first graph given here, we have x-axis and y-axis with the points marked as -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5 and 6 along x-axis, and points marked along y-axis are -3, -2, -1, 0, 1, 2 and 3. We also have a line for y is equal to 1 upon 2x being plotted on this graph paper. In the next picture, we have again the points marked along the x-axis vary from -6 to +6 and on y-axis from -3 to +3. We also have the graph of a line which is representing y is equal to x. In the next picture, in figure 2.8, we have the points marked on x-axis between -6 to +6 and on y-axis between -3 to +3. We also have the graph of a line representing y is equal to 2x. Page number 31. Figure 2.9 displays all the 3 graphs on the same axis. Does this help you to conclude anything about the linear equation y is equal to ax, where a is greater than 0 as a varies. What happens when a is greater than 1 and when a is less than 1? The hint provided is you may also plot the equations y is equal to 3x and y is equal to 1 upon 3x on the same axis. In figure 2.9, we have a graph sheet on which the three lines have been plotted. On x-axis, we have the markings ranging from -6 to +6, and on y-axis, the markings were ranging from -3 to +3 on y-axis. We also have graphs of all the three equations, that is y is equal to 1 upon 2x, y is equal to x, and y is equal to 2x, drawn on the same graph. First of all, we observe that the straight lines representing an equation of the form y is equal to ax always pass through the origin 0, 0. Further, when a is greater than 1, the line is steeper than the line y is equal to x, which is equally inclined to both axes. However, when a is less than 1, the line is less steep than the line y is equal to x. In fact, a is referred to as the slope of the line y is equal to a into x. We will learn more about the concept of the slope of a line in the chapter on linear equations. For now, we focus on another important observation. A linear growth is represented by a straight line with positive slope, while a linear decay is represented by a straight line with negative slope. Note that the number of square tiles in the pattern in figure 2.4 leads to the sequence 1, 3, 5, 7 and so on, in which the difference of consecutive terms is the constant 2. The slope of the line representing the linear relationship between the term number and the number of square tiles is y is equal to 2x minus 1 is 2. Hence, the slope represents the constant difference between consecutive terms of the sequence. Example 15. Now let us draw the graphs of y is equal to minus 1 upon 3x, y is equal to minus x, y is equal to minus 3x by selecting suitable points on these lines. Figure 2.10 displays the graphs of these linear equations without any points labeled on them. Page number 32. In figure 2.10, we have three graph papers here. On first graph paper, we have the markings on x-axis ranging from -7 to +7 and the markings on y-axis ranging from -4 to +4. We also find graph of the line y is equal to -1 upon 3x on this graph sheet. In the next picture, we have again the markings on the x-axis ranging from -7 to +7 and on y-axis the markings are ranging between -3 to +4. And we also have graph of the line y is equal to -x. In the next picture, we have again the markings on x-axis marked between -7 to +7 and the values of y ranging from -1 to +4 on y-axis. We also have graph of the equation y is equal to minus 3x on this graph sheet. Page number 33. Figure 2.11 displays all the three graphs on the same axis. Does this help you to conclude anything about the linear equation y is equal to minus of ax? A is greater than 0 as a varies. What will happen when a is greater than 1 and when a is less than 1? In figure 2.11, we have a graph sheet on which we have the markings on x-axis ranging from minus 7 to plus 7, and on y-axis the values marked are between minus 4 and plus 4. We also can find the graphs of three equations on the same graph for equations y is equal to minus 1 upon 3x, y is equal to minus x, and y is equal to minus 3 into x. Think and reflect. Differentiate between the graphs of the equations y is equal to 3x plus 1 and y is equal to minus 3x plus 1. Example 16. Let us now draw the graphs of y is equal to 2x minus 1, y is equal to 2x plus 1, y is equal to 2x plus 5. First individually as displayed in figure 2.12 and then on the same axis as displayed in figure 2.13. Here in figure 2.12a, we find the graph of the equation y is equal to 2x minus 1 drawn on the graph sheet. Page number 34. In figure 2.12b, we have the markings on x-axis ranging from minus 6 to plus 7, and on y-axis the markings are between minus 2 to plus 5. We can also find the figure of the equation y is equal to 2x plus 1 drawn on this graph. In figure 2.12c, we have the markings on x-axis to be between minus 6 to plus 7, and on y-axis the values marked are between minus 2 to plus 5. We also have graph of the equation y is equal to 2x plus 5 represented on this graph sheet. In figure 2.13, we have the markings of x-axis ranging from minus 6 to plus 7 and the values on y-axis to be ranging from minus 2 to 5 on the y-axis. We can also find the graphs of all the three equations on the same graph here. First one, y is equal to 2x plus 5, then y is equal to 2x plus 1, then y is equal to 2x minus 1. Page number 35. Think and reflect. Does this help you to conclude anything about the linear equation y is equal to ax plus b, where a is fixed but b varies? The hint provided is, in these equations a is equal to 2 and b takes the values minus 1, 1 and 5 respectively. Now let us draw the graphs of the equations y is equal to x plus 3, y is equal to 2x plus 5 and y is equal to 3x minus 2. Observe figure 2.14 and observe where these lines cut the y-axis. In figure 2.14, we have the markings on x-axis to be ranging from minus 3 to 6, and on y-axis we have the values marked between -2 to +7. And we also have graphs of the equations y is equal to 2x plus 5, y is equal to x plus 3 and y is equal to 3x minus 2. Y is equal to 2x plus 5 cuts the y-axis at a 0, 5. Y is equal to x plus 3 cuts the y-axis at b 0, 3. And y is equal to 3x minus 2 cuts the y-axis at c 0, minus 2. We observe that any straight line written in the form y is equal to ax plus b cuts the y-axis at the point 0, b. The length b is referred to as the y-intercept of the line. Thus, the y-intercept of the line y is equal to x plus 3 is 3. This means that the line cuts the y-axis at a distance of 3 units from the origin in the positive direction. Similarly, the y-intercept of the line y is equal to 3x minus 2 is minus 2. Page number 36. This means that the line cuts the y-axis at a distance of 2 units from the origin in the negative direction. After observing the graphs in figures 2.8 to 2.14, we may conclude the following. First point, in the equation y is equal to ax plus b, a represents the slope of the line and b represents the y-intercept. Second point, if we change the values of a, keeping b fixed, the slope of the line changes while the y-intercept remains fixed. Third point, if we change the values of b, keeping the values of a fixed, the lines shift but remain parallel to the original line. Thus, lines with equal slopes but different y-intercepts are parallel to each other. Exercise set 2.6. Question number 1. Draw the graphs of the following sets of lines. In each case, reflect on the role of A and B. First part, y is equal to 4x, y is equal to 2x and y is equal to x. Second part, y is equal to minus 6x, y is equal to minus 3x, y is equal to minus x. Third part, y is equal to 5x, y is equal to minus 5x. Fourth part, y is equal to 3x minus 1, y is equal to 3x, y is equal to 3x plus 1. Fifth part, y is equal to minus 2x minus 3, y is equal to minus 2x, y is equal to 2x plus 3. End of chapter exercises. Question number 1. Write a polynomial of degree 3 in the variable x in which the coefficient of the x squared term is minus 7. Question number 2. Find the values of the following polynomials at the indicated values of the variables. First part, 5x square minus 3x plus 7 if x is equal to 1. Second part, 4t cube minus t square plus 6 if t is equal to a. Page number 37. Question number 3. If we multiply a number by 5 upon 2 and add 2 upon 3 to the product, we get minus 7 upon 12. Find the number. Question number 4. A positive number is 5 times another number. If 21 is added to both the numbers, then one of the new numbers becomes twice the other new number. What are the numbers? Question number 5. If you have 800 rupees and you save 250 rupees every month. Find the amount you have after first part 6 months, second part 2 years. Express this as a linear equation, as a linear pattern. Question number 6. The digits of a two-digit number differ by 3. If the digits are interchanged and the resulting number is added to the original number, we get 143. Find both the numbers. Question number 7. Draw the graph of the following equations and identify their slopes and y-intercepts. Also, find the coordinates of the points where these lines cut the y-axis. First part, y is equal to minus 3x plus 4. Second part, 2y is equal to 4x plus 7. Third part, 5y is equal to 6x minus 10. Fourth part, 3y is equal to 6x minus 11. Are any of the lines parallel? Question number 8. If the temperature of a liquid can be measured in Kelvin units as xk and in fan heat units as y degree F, the relation between the two systems of measurement of temperature is given by the linear equation y is equal to 9 upon 5 into x minus 273 within brackets plus 32. First part. Find the temperature of the liquid in fan heat if the temperature of the liquid is 313 Kelvin. Second part. If the temperature is 158 degree fan heat, then find the temperature in Kelvin. Question number 9. The work done by a body on the application of a constant force is the product of the constant force and the distance travelled by the body in the direction of the force. Express this in the form of a linear equation in two variables, work W and distance d, and draw its graph by taking the constant force as 3 units. What is the work done when the distance travelled is 2 units? Verify it by plotting it on the graph. Page number 38. Question number 10. The graph of the linear polynomial p of x passes through the points 1, 5 and 3, 11. First part, find the polynomial p of x. Second part, find the coordinates where the graph of p of x cuts the axis. Third part, draw the graph of p of x and verify your answers. Question number 11. Let p of x equal to ax plus b and q of x is equal to cx plus d be two linear polynomials such that first part, p of 0 is equal to 5. Second part, the polynomial p of x minus q of x cuts the x-axis at 3, 0. Third part, the sum p of x plus q of x is equal to 6x plus 4 for all real x. Find the polynomials p of x and q of x. Question number 12. Observe the first 3 stages of a growing pattern of hexagons made using matchsticks. A new hexagon gets added at every stage, which shares a side with the last hexagon of the previous stage. In stage 1, we have the picture of one hexagon. In stage 2, we find two hexagons sharing one common side. In stage 3, we have three hexagons in which one hexagon shares one hexagon on one of its side for the either of the hexagons. First point, draw the next two stages of the pattern. How many matchsticks will be required at these stages? Second part, complete the following table. Here we are provided with a table in which we have stage number, number of matchsticks mentioned. Stage numbers are 1, 2, 3, 4, 5, so on till n. And you are expected to fill up the number of matchsticks in these blank boxes. Third part, find a rule to determine the number of matchsticks required for the nth stage. Page number 39. Fourth part, how many matchsticks will be required for the 15th stage of the pattern? Fifth part, can 200 matchsticks form a stage in this pattern? Justify your answer. Question number 13. Let P of x be equal to ax plus b and q of x be equal to cx plus d. Be two linear polynomials such that first part, the graph of P of x passes through the points 2, 3 and 6, 11. Second part, the graph of Q of x passes through the point 4, -1. Third part, the graph of Q of x is parallel to the graph of P of x. Find the polynomials P of x and Q of x. Also, find the coordinates of the point where these lines meet the x-axis. Question number 14. What do all linear functions of the form f of x is equal to ax plus a, where a is greater than 0, have in common? Chapter summary. An algebraic expression combines numbers, variables, and operation symbols. For example, 2x square plus 5xy minus 3y square is an algebraic expression in the variables x and y. 2x square, 5xy and minus 3y square are the terms of the algebraic expression, and the numbers 2, 5 and minus 3 are coefficients of the terms. Univariate polynomials are algebraic expressions in one variable. Thus, x square plus 5x plus 3 and 3y cube minus 4y square plus 5 are univariate polynomials in x and y, respectively. The highest power of the variable in a univariate polynomial is called its degree. Thus, x square plus 5x plus 3 is of degree 2, while 3y cube minus 4y square plus 5 is of degree 3. A polynomial of degree 1 is called a linear polynomial. Hence, 2x plus 3 and 5 minus 4y are linear polynomials in the variables x and y, respectively. Linear growth refers to a pattern in which a quantity increases by a fixed amount over equal intervals. In contrast, linear decay describes a pattern in which a quantity decreases by a fixed amount over equal intervals. Page number 40. A linear pattern is a sequence of numbers where the difference between consecutive terms is constant. A linear relationship between two variables x and y is represented by a straight line y is equal to ax plus b. The slope of this line is a. The constant b is called the y-intercept, which is the distance from the origin where the line cuts the y-axis. When b is equal to 0, the equation of the line becomes y is equal to ax, and the line passes through the origin. Linear growth is represented by a straight line with positive slope, and linear decay is represented by a straight line with negative slope. Parallel lines are of the form y is equal to ax plus b, where the slope a is fixed, while b, the y-intercept, varies. Chapter 2 ends here.
Ganit Manjari, Part 1. You were just listening to this audiobook, Textbook of Mathematics for Grade 9. Narration Swarnlata Sharma. Sound recordist Mohammad Faizan Khan. Assistance in production Arshad Ahmad. Directed and produced by Vimlesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.